in this lecture we continue with a discussion on placement issues in VLSI physical design. So, in this second part of the lecture, first we talk about some of the design style specific issues in placement. Now, I have repeatedly mentioned earlier also that many of the steps in VLSI physical design depends very much on the exact design style that you are following in creating your final layout. Well, it can be a full custom, it can be semi custom, standard cell based, it can be gate array or FPGA based and so on. So, here we shall see that with respect to placement, how the choice of the design style can impact or can affect exactly what we want to do or what we intend to do during the placement phase. So, the main issues that arise out of the placement problem, this depends on the design style used. You see, this also I mentioned earlier that in the standard cell design style, for instance, the floor planning and placement problems are the same, because you just recall that in a standard cell based design, the places where you can put a cell are limited. It is only along the rows in which you can place the cells. So, when we talk about floor planning, you are tentatively assigning a location for the cells. Now, that location itself will have to be within one of those rows. So, once you put a cell in one of the rows, well, you are as well completing the placement also, because placement will also mean the same thing, placing the cell in one of the rows. Okay. So, here there is one design style example where floor planning and placement does not make any difference actually, right. So, we discuss the ASIC design styles, in particular full custom, standard cell and gate array, and the main issues involved therein for placement. So, we start with full custom. Now, in full custom we have seen that this is a completely unrestricted kind of a design style. Here you have the silicon floor and you can place any block anywhere you want to, and also the shapes, the sizes, the aspect ratios of the blocks can vary. Okay. There is no restriction per se. Of course, you can mix the other design styles also, some part can be standard cell based, some part can be full custom based, etc. But in general, for full custom based design style, this is true. So, the placement problem will consist of placing a number of blocks of various shapes and sizes within the layout area that is available to you. Now, the block shapes may not be very regular, because of which some area may remain unused. For full custom design style, I mentioned earlier also that explicitly you require both the floor planning and the placement steps. But however, depending on the algorithm that you are using, you may need several iterations where you may start with a particular placement and you try to successively improve the quality of the placement in an iterative process, where at every step you are modifying the layout a little bit. Now, the floor planning and placement steps are required for full custom. Let me just repeat it once more, what exactly we mean by that. Let us take an example again. Let us say we talk about floor planning. There is a block A, there is a block B, there is a block C and D. This is one instance or example of a floor plan for these 4 blocks. Now, again when we move to the next step of placement, now the exact shapes and sizes of the blocks have been defined, and also you have to keep some extra space for routing. So, now your placement may look like this. This will be your block A, this can be your block B, your block C might look like this, your block D might be smaller, let us say like this. So, here you see in this example of a placement, this is a placement. So, in this example of a placement, you have explicitly kept some spaces between the blocks and also around, using which you can complete the routing or the interconnections, right. And also you see, because of the unevenness of the shapes and sizes of the blocks, there are some areas like here which are unused. So, you are not really using this part of the area. Okay. So, this is one of the properties of placement in full custom design, that there can be some area which is wasted. Okay. Next, let us come to this standard cell design style. So, here as I had mentioned, here also the problem of floor planning and placement are the same. So, again let me just clarify this point. So, in this standard cell design style, your layout area will look like this, where there will be several rows in which you are expected to put in the standard cells one by one. So, I am showing 2 rows. Now, suppose I have some standard cells. So, one shape like this, like one little less wide. So, I want to put them somewhere. So, in the floor planning, so I have to find out a tentative place for these blocks. Let us call this block 1 and let us call this block 2. Suppose I decide to put my block 1 out here during the floor planning phase. Block 2 I may decide to put here. Now, you see, during floor planning, because of the constraint in the design style, we are forced to plan these blocks to be placed only along the standard cell rows. In the placement also we have to do the same thing. They say these are the only places where you can place the blocks. So, what you have done during floor planning is exactly what you need to do during placement also. Okay. So, the two problems are the same in case of standard cell design. Now, here of course, your objective will be to minimize the overall layout area. Layout area means well, you have to allocate the blocks in such a way that your interconnection complexity is minimized. That means, the number of tracks you require to interconnect, that means the channels, minimize some of the channel heights. Like again coming back to this diagram, channel height is this. This is the place where the interconnection wires will be laid out, and depending on how many tracks will be laid out here, the height of the channel will be fixed according to that, right. So, one objective will be to assign the blocks in such a way that you require less number of tracks, therefore, the height of the channel will be less. And of course, you want to minimize the width of the widest row. Like in the standard cell design, it is desirable that all the rows are of the same width. That will provide you with an optimum utilization of the area. But again, there can be slightly unequal blocks at the end. So, there can be little mismatch. So, even if there is a little mismatch, there should not be too much difference between the widths. You are trying to minimize the widest row in the standard cell layout. Okay. This is what I mentioned. And the last point, there is something called over the cell routing. This is also an option in sophisticated routing algorithms. Here you can get something called almost channelless designs. So, what this means, let me just try to tell you with the help of this diagram again. Now, you see in this diagram you have kept a separate area for the interconnections. So, as I said, in this case what you do, you lay out the horizontal and the vertical lines on two different layers and you complete the connections like this. Now, these connections are created on metal layers which are typically on a higher layer surface as compared to the actual transistors which have been fabricated down below using the polysilicon diffusion these layers. So, the metal layers are anyway means they are created on a layer which is above the transistors. Okay. So, because they are above the transistors, so no one is preventing you from creating interconnections like this. Let us say from a point here you can make an interconnection like this, means over the cell you are drawing the interconnection lines above the cell on a different layer of course. This is called over the cell routing. Now, if you can complete your routing, I mean in this way, in the over the cell manner, then you do not need this separate channel at all. So, you will be getting virtually a channel less layout of standard cell which will be much more compact again. Okay. Fine. So, continuing with the next one, gate arrays. Gate arrays, here what you have? You have an array of gates. So, when you do partitioning, you are creating the partitions, you are trying to put each of the partitioned elements somewhere. Floor planning, you are doing the same thing. Placement also you will be doing the same thing. So, ultimate goal of all these steps will be to place a gate into a particular location in the gate array. So, for gate array design style, the partition, floor planning, placement, all these three can be merged together. They really do not mean anything different. But for FPGAs, however, the problem is slightly different. So, here you are not mapping a particular gate, like let me take an example for an FPGA design. Suppose I have a circuit netlist like this. So, I am taking an example. Suppose I have a circuit like this. There are several gates here. Now, suppose I want to map it into an FPGA where we have 4 input lookup tables, right. So, as I said, for this kind of a scenario, it is not that you are mapping one gate into an LUT, but any general circuit or sub circuit which will be having 4 inputs and 1 output can be mapped into an LUT. So, in this example, for instance, you can map this part of the circuit into one LUT, let us call it LUT 1, and the remaining part again which will have 3 inputs and 1 output into the second LUT. So, the mapping for FPGAs is much simpler. So, you take your netlist tree and from the netlist tree you actually find out sub circuits from the graph which will be having up to 4 inputs and 1 output and do some kind of graph partitioning. So, there are many good algorithms for graph partitioning which exists, right. So, this is what is done for FPGAs. Now, talking about the placement algorithms, the placement algorithms can be classified into broadly these classes. One are based on simulation based, simulated annealing, simulated evolution or genetic algorithm, force directed placement. This is also a very interesting method, we shall be looking at this. There are methods where you are creating placement out of partitioning process. There are methods like Brewer's algorithm and some modification terminal propagation, and there are some other methods also. Cluster growth is force directed, also you can categorize in the other category. So, it can be used to create an initial cluster, which can be cluster or means some kind of initial placement, which can be improved during the simulated annealing process, for example, right. So, let us see some of these algorithms. Simulated annealing is an algorithm which has been very popular with respect to the problem of placement. We had talked about simulated annealing earlier also. Let us spend a little time to recall what we had said about simulated annealing, and let us see how we apply this tool, you can say tool or algorithm, whatever you say, to this particular problem of module placement. Okay. So, simulated annealing, I mentioned this, that this is a process which simulates the annealing process in metals or glass. So, when we create metal or glass crystals, what you do? We melt the material to a high temperature where it is converted into liquid, and then we follow a cooling sequence. We slowly cool the liquid state, that material, and the material will be finally crystallizing and will take the shape of the material that we want it to have. Okay. So, the thing is that at high temperatures, the atoms and molecules are very volatile, they are moving around very fast, but as the temperature is going down, they are getting more and more stabilized. So, something similar is done here, some analogy is drawn, that initially things might change, but as you move in time, things will become more and more stable. Okay. So, the kind of analogy that is drawn is like this, that you start with an initial placement. Well, that may represent that initial liquidified state of the material. You start with an initial placement which you want to improve. Then you define a number of moves, like for example, exchanging two blocks, moving a block from one position to another, changing the orientation of a block, etc., which might result in incremental improvements. So, if you get an improvement, you accept it. Moves which decrease the cost are always accepted. But however, if you find that you make a move, but the cost is increasing, so it is not that you will always be rejecting such a move. So, you can reject that move, but that move will be accepted with a probability that decreases with the number of iterations. This strategy helps in avoiding the process getting trapped in a local minima. Like you see in any optimization problem, so usually for complex problem you will be having a behavior like this, cost with time. So, as you carry out the optimization, you may find that your cost is decreasing, again increasing, again decreasing. So, there can be several minimum points. So, if you are say here and you are using a purely greedy approach to decrease the cost, then you will get stuck here. But if you follow some worse moves, it is likely that you may make a move in this direction. So, you move in the other side and you can possibly fall in this valley and reach this solution which has a even lower cost. Okay. This is the basic idea behind saying that you are avoiding local minima. These are local minima points. Okay. Now, the another thing is that I said that you accept the worst moves with a probability that decreases with time. So, how do you implement this? See, you implement this in this way. Well, in terms of programming, you can keep a variable that represents the temperature. Let us say I start by initializing this temperature to high value, let us say 100,000, right. and at the end of every iteration I modify the temperature, let us say T equal to T multiplied by let us say 0.95, let us say. So, in every step I will be decreasing this temperature progressively, like it was 100,000, after one iteration it will be 95,000, after second iteration it will be even less, and so on. So, if you plot temperature versus time, this will also go down following certain slope of this curve depending on this multiplication factor. And in between you can use a parameter, let us say e to the power minus alpha into t, alpha is a constant. So, you accept a worse move with probability this. So, you see as the t is high, what this probability means, e to the power minus a very small number. So, it is this number is actually close to 1, but as temperature decreases this will become less and less. So, it will be this probability will actually go down. So, the idea is that means initially towards the initial parts of the iteration you are saying that you may accept worse moves many a time, but as time progresses the temperature drops. So, here we shall be reducing that probability, the chance of accepting a worse move becomes less and less. Okay? This is the idea. So, one of the very popular simulated annealing tool that was developed was called Timberwolf. In fact, there was a point in time where Timberwolf was the best known placement algorithm, and it was mainly used for creating placement for standard cell based designs, but of course, it can be used for general full custom designs also. Okay. Let us see how Timberwolf works. This is the overall pseudo code of this simulated annealing process or algorithm. Let us see the different steps. As it said, we use a variable T indicating the temperature. We initialize it with some large value, like the example I said 100,000, that will be the initial temperature, and we start with an initial placement of the blocks. So, initially we can start with a random placement maybe, or some placement which has been created through some kind of intelligence, we will see those later. Now, in this while loop, so I can create a final temperature, I can define a final temperature, let us say final temperature I can define as 0.5. So, in every iteration I am reducing the temperature T equal to schedule T, this can be as I said T equal to T multiplied by 0.95. So, T is decreasing. So, at one point in time T will be less than the final temperature, then you will be going out of the loop, otherwise you will be repeating. Now, at every temperature value T, you are carrying out a number of inner loops or iterations, while number of trials at each temperature not yet completed. Let us say you decide to create 100 trial moves in at every value of T. So, for every value of T, the inner while loop will be looping 100 times. So, what you do? You make a trial move, you call a function called perturb, which makes small changes to your placement P, that will be your new placement. Okay. So, you have a cost function, you apply it to your new placement and also the original placement, and see the difference delta C. You see, if delta C is negative, that means you have found out a better placement. So, you accept it and make it as your P, replace P by this new placement. But otherwise, if your cost is increasing, is positive, then you use a function like this. If a random number between 0 and 1, generate a random number, is greater than e to the power delta C by T, this creates that condition that if your probability towards the initial part of iteration is larger, but as t increases the probability will be smaller. This condition takes care of that. So, with this probability if the random number is greater than that, then only you accept this worst move and you repeat this process. Okay, it is very simple, the process is very simple, right. So, in Timberwolf the initial temperature was set to 4 million, final temperature was 0.1. The schedule was not as simple as I said 0.95 into T, but it was some multiplicative factor which changes with time. Like when the cooling process just starts, you start with alpha T equal to 0.8, but in the medium range of the temperature you make it 0.95. Towards the end you again make it 0.8. So, what will happen is that the cooling sequence will actually be like this. Initially it will be cooling at a certain rate, then it will be leveling up, then again it will be cooling at the other rate. So, it will be something like this, temperature versus time curve. So, this has been decided or arrived upon through experimentation. So, by using various different kinds of this schedule function, the authors Sechin and Sanjeevani Vincenteli they found that this kind of a function works the best for placement. So, in the part of function they used 3 different means alternate moves, this M1, M2 and M3. This M1 indicates you displace a block, a randomly selected block to a new location. See, this block and also the new location, both of these are typically selected randomly. The second move M2 says you pick up 2 random blocks, you interchange their locations. The third move says you pick up a block at random, you change the orientation. Orientation means you take a mirror image. Mirror image means you have a block, you either take a mirror of it in the x direction, rotate it in the x direction, or rotate it in the y direction. Well, rotating in the y direction is applicable for full custom design. For standard cells you really cannot do it, because you recall in standard cells VDD runs on the top and ground runs on the bottom. If you rotate in this way, ground will go up and VDD will go down. Okay? But for general full custom you can do this. Okay. All right, fine. And these moves M1, M2, M3 are chosen at random again, and M3 is chosen the way it was done, that only when this M1 whatever you are trying to do, this was rejected. For example, you randomly select a new location to move, but you find that already the new location is occupied, you cannot make the move, then only you try out M3. Okay? This was the strategy which was followed. So, some illustrations. These illustrations are for standard cells. This M1 move says, so I pick up a block at random, I move it to a new location, let us say this block will be moved here. This M2 says, I can pick up 2 blocks at random, say this and this, and if space permits I will exchange them, I will bring this block here and I will bring this block here. And M3, as I said, if I have a block like this, I will take a mirror image, that means 1 is the left, 2 is the right, it will become 2 or 1, or I can also reflect it along the y direction. So, this 3 4 will remain 3 4, but vertically its orientation will get changed. Okay? So, the block will get rotated in this fashion. All right. But again I said for standard cell this kind of vertical rotation does not make a sense. This rotation is, this will be allowed only for full custom design style placement for there. Okay? Fine. Now, selection of the moves was done like this. First, Timberwolf selected a move between M1 and M2, where the probability of M1 was 80%, 4 by 5, probability of M2 was 20%, 1 by 5. Now, as I said earlier that if you select M1 and if it is rejected, that means you cannot move it, then a move of type M3 is done with probability 0.1, 10% probability. But when you make the moves, also there is something you want to look at. There are some restrictions you want to impose, how far a module can be displaced and what pair of module can be interchanged. Like as I said, to simulate the properties of the annealing process, initially I am allowing lot of volatility. Blocks may move over longer distances, but as time progresses, I will not allow such random or drastic moves. Only blocks in the closer vicinity can move around. Okay? This is the idea. So, here we use some kind of a range limiter. The idea is this: range limiter is like a rectangular region, like you imagine a rectangular space, rectangular window. So, initially you start with this R which covers the entire layout area, which means the moves are allowed anywhere within R, but as the iterations progress, the size of the R will become smaller and smaller. So, the range, like in one stage it can be this much, that means only you can move within this region indicated by this rectangular area, not beyond that. Okay. So, window size shrinks as the temperature decreases. Okay. So, this is the idea. So, the cost function, there are three components to it. First one is the weighted sum of the estimated length of all nets. We have already seen earlier how to estimate the cost of the nets. Cost 2 is during placement you are not here, you are not actually disallowing overlapping, but you know that overlapping is not allowed. So, instead of disallowing overlapping, what you are doing, you are saying that blocks can overlap, but the penalty for overlapping will be a very high cost. So, anyway when you are minimizing cost, the overlapping cases will get eliminated automatically. Okay. So, cost 2 is the penalty cost for overlapping and cost 3 is the penalty cost for uneven length across the different standard cell rows, because you want that all rows must be approximately of the same width, but if there is a difference you incur a penalty of cost 3. Okay. So, this is what I mentioned, the cost function cost 2 penalizes the overlapping and similarly cost 3 penalizes the unequal lengths of the rows. So, to summarize, Timberwolf was one of the very successful placement tools that was used for standard cell based designs, but this with some modification can also be used for the other design styles like full custom. So, we come to the end of this lecture. In our next lectures, we shall be looking at some other techniques or algorithms for placement.